I'm Marc Ivaldi, professor of economics at Toulouse School of Economics. I'm also the conference director in charge of organizing the next World Conference on Transport Research, WCTR for the acronym. Conference that will gather more than 1,500 researchers from all over the world and from all domains of research in transportation in Toulouse from the 6th to the 10th of July 2026. On the road to this major event in transport research, we thought it was useful to organize a panel on sustainable aviation to prefigurate the intellectual exchange that will be at the core of the WCTR. To open this panel, I'm pleased to invite Professor Tae-Hoon, President of the World Conference on Transport Research Society, WCTRS for the acronym, to welcome you. So, dear Tae, please, you have the floor.
Thank you very much, Mark. Ladies and gentlemen, and the distinguished guests, it's an honor to welcome all of you, to this important forum on sustainable aviation. First, I would like to extend my sincere thanks to Professor Marc Ivaldi, WCTR 2026 Conference Director, to be held in Toulouse in 2026. And to also my thanks to Professor Christian Gollier, Director of the TSE, Toulouse School of Economics, for his support and the contributions. The WCTR Society is dedicated to advancing sustainable transport solutions in all modes of transportation. Today's forum is an important step toward that goal, achieving that goal. Of course, Toulouse, with its rich expertise and the achievements in aerospace, is the ideal place to explore the future of greener air transport. We are, of course, privileged to have leading experts here today, including Sabine Clark, Chief Technology Officer of the Airbus, leading person whose leadership is in decarbonization technology is inspiring. And of course, the Thierry points out from Toulouse fluid mechanics with glaring global recognition and qualifications. Achieving sustainable air transport will require technological development, proper policy, and industry cooperations. And forums like this lay the foundation for such progress. As my final words, I warmly invite you to join us in Toulouse in 2026 World Conference. Together, let us create the future of sustainable transportation, including sustainable aviation. Thank you very much.
Thank you very much, Professor Tae-Hoon, for your presence among us today. Well, you are addressing us online from Western Canada, so at a very early hour of the day for you. I'm now pleased to welcome my colleague, Professor Christian Gollet, who is a well-known economist of climate change and director of Toulouse School of Economics. So Christian will moderate the panel, and so Christian, you have the floor.
Okay, thank you very much, Mark, and I'm very happy to moderate this short session, 55 minutes, on this very crucial issue of decarbonization of the aviation sector, crucial for Toulouse in particular, but also crucial for the world, given the fact that the aviation sector represents something like 8% of the world emissions of CO2. So for this panel session, I have three distinguished panelists. Let me introduce them before starting the discussion. So first, we have Sabine Klok, who is, as you just mentioned it, Chief Technology Officer at Airbus. We have Thierry Poinçon, who is leading researcher in Institut de Mécanique des Fluides de Toulouse. And of course, we have you, Mark, my dear colleague from the Toulouse School of Economics. So let me start with you, Mark. So, Mark, you are an emeritus professor of economics at TSE and at École des Hautes Études en Sciences Sociales. You are the president of the French Association of Transport Economics. You are an expert in the use of empirical and quantitative methods for competition and regulation policy, and you are advising firms as well as public authorities on the wide range of issues in Israel organization. Much of your work has been devoted to the analysis of network and transport service industries. So, Mark, could you summarize for us what are the environmental challenges that the aviation is facing right now?
So let me share my screen. Is it okay?
Yes.
So thank you, Christian, for the question. That is going to allow me to briefly present the context of the panel discussion. Aviation is perceived as a major source of pollution. Aviation is often making the headlines of press and TV media, and it's often involved in the debate on the causes of climate change. It is charged as consuming too much fossil energy, designed only for rich people and countries, and the main driver for over-tourism. And aviation has been even issued the feeling of shame that has been named flag scam because it was initiated in Sweden. So the first question is to know whether or not aviation is a major source of pollution. As a matter of fact, aviation accounts for only 3% of carbon emission. On this picture indicates that all types of transport represent 1/3 of carbon emission in the European Union, which is a lot. Road transport by individual car is responsible for 2/3 of this emission due to transport. And we observe that aviation, like maritime, represent only a very small part of the emission due to transport within the European Union, and most of the emission due to air transport are related to international transportation. So it is also interesting to notice that aircraft have experienced tremendous improvement in terms of fuel efficiency. On this graph, the blue line exhibits an impressive increase in the traffic that has been multiplied by 10 in around 40 years. The growth in traffic has been, of course, accompanied by a significant increase in CO2 emissions. Let's forget on this graph the last year, they correspond to the COVID period. Since then, the traffic has raised again. Now, the red line shows the increase in fuel efficiency of aircraft expressed in terms of emission per revenue passenger kilometer. So fuel efficiency has experienced at least a 3% growth on average each 10 years, which is quite substantial. This is because the DNA of our aeronautical engineers is to design aircraft that are lighter and less costly to operate. It turned out that the main sources of CO2 emission from aviation are coming from a long-distance flight. This graph shows that 53% of aviation emission are due to flight of a range more than 3,000 kilometers, will represent only 9% of all flights from and to Europe. Given that there are flights, given there are almost no substitute to aviation on such a flight, there is not much we can do for this domain of transportation. If we consider all flights on a range less than 1,000 kilometers, it concerns only 15% of aviation emission. So that on this range, we cannot expect that a substitution to the train will have a large impact to reduce carbon emission. So there is a contrast between these figures that describe the real impact of aviation in terms of CO2 emission and the perceived impact of aviation. This is because it remains that aviation faces a major environmental challenge, because it remains that aviation is the highest emitters of emission among transport modes. This slide shows that during a journey in an aircraft, a passenger emits each kilometer 300 grams of CO2, which is twice what this passenger will emit if he or she is traveling in an individual car, and 20 times if he or she is comfortable seated in a train. Moreover, there is no reason to expect that the growth of aviation traffic will stop in the next decade, because there are many countries in the world where aviation is going to be adopted by more and more people to travel and to change places, notably in emerging countries where air transport is still in its infancy. So here is a slide showing that one still expects an annual 4% traffic growth until 2050. So if nothing is done, aviation emission will keep growing, as the red line shows. So discussing the solution and creating the future of sustainable aviation is on our research agenda. I can give you the floor, Christian.
Thank you very much, Marc. So let me Let me now move to Sabine Cloak. Sabine is the CTO, as I said earlier, CTO of Airbus, and leads a team of over 13,000 employees responsible for designing, developing, and certifying commercial aircraft products and services. She also holds several other positions, including co-chair of the Clean Aviation Joint Undertaking and vice president of aviation for the German Aerospace Industries Association. Sabine's career at Airbus began in 2002, and she has held various positions of increasing responsibility within the company. Before joining Airbus, she worked for Delmia, a brand of Dassault Systems from 1998 to 2002. So Sabine, could you tell us what's the roadmap to decarbonize aviation based on the technologies developed by Airbus?
Yeah, thank you for the introduction, Christian, and for the question. I think there might be some slides as well. I don't know if somebody is putting them in, but let's see how we get there. So as we have heard, yes, aviation is responsible for a part of the CO2 emissions, and decarbonizing the aviation sector is a very ambitious goal. So to achieve that, we don't have one only technology of which we can actually use, but we need to take that in a multifaceted path where we pull basically 4 levers at the same time to get there over time as well. So if we briefly look at it, between the reduction of CO2, which we can have by aircraft, by passenger seat kilometer, as we've seen, and the growth which is ongoing, we really need to act on different sizes. So on one hand, it is about increasing the efficiency of the current aircraft and continuously improving them, as well as renewing the global fleet with the most recent standards of aircraft. Secondly, it is about improving the flight operations and making them in the surrounding system more and more efficient. But also, a huge part is coming from scaling sustainable aviation fuels. So it is as well about the fuel type that we are using. And fourth, last but not least, it's as well about looking into disruptive technologies into the future, which could bring us to a different profile of energy, of propulsion, and hence on emissions as well. So if you look into the 4 pillars, let's look into the continuous improving system of an aircraft, the efficiency. That is a story, as we have seen, which is going on for over 50 years. And if we look today, the latest generation aircraft, which we've just certified, it's a new family member of the A320 family. So A321 extra long range, we call it. It saves 30% fuel compared to previous generation aircraft. And the engine, of course, has a very big part of it. So this is opening really a big step for the airlines. So that means more we do the fleet overhaul, the more we get these improvements into the worldwide fleet. So today, still around 75% of the fleets are actually older generations. So there's something to do here. As well, if you look at an aircraft, then all the components are up for improvement. So if you think about the next generation, we would still work on more efficient engines. We also would work on novel wing concepts with potential, we call our projects Wing of Tomorrow, extra performance wing, where it's really about reduced weight through different materials, but also about far different aerodynamic shapes of the wings, up to foldable wingtips, which would then increase the efficiency further. So there's a lot to do in the technologies we take on the aircraft. If you come to the second pillar, I talked about operations. So how can we leverage flight operations? So first of all, there is a lot to do by sensing technologies, digitalization, AI. And I just want to give you two examples here. One is actually taking examples of the biology. If we look at geese flying, transitioning, and they do that in this V shape, and we can actually position aircraft in formation flights, especially if it's about long haul flights, where we can save 5 to 10% fuel. And of course, here we need to automatize this kind of coupling. Yeah? So in the case of a long range flight, this would be 3 kilometers distance. But still, you need to then be sure that you stay in the right positioning in order to take the vortex from the aircraft which is flying in front. Another example here is about what we call digitalized air traffic management. So if we manage to actually get rid of the waiting lines, have a better planning, introduce the aircrafts into more direct flights, that can save up to, let's say, 1.6 tons CO2 per flight in the future. And this, of course, is as well really interesting in the very congested shorter haul flights that we all know here in our cities and airports in Europe, but overall over the world. And that's a bit, if I compare that just sheer figure of 1.6 ton, that is like 1 year of commuting by car. So you've given us a couple of comparisons. So that's the size. The third pillar, sustainable aviation fuels. And here, if we would switch to 100% sustainable fuels, we could reduce the emissions by 80%. So basically, it's a netting game. Today, every aircraft can use up to 50% sustainable aviation fuel already in a blend. So we are going into a certification towards 100% so that we can really have the fleet ready for that by 2030. But there is a big challenge on the availability of these fuels. We have doubled production in 2024 worldwide, and still we only reach, I think it's the last figure is 0.3% of the global fuel production. So that's kind of like 1.5 spoon for a 100-kilometer drive in a car. So you can see the relations which are not yet the good ones. So here, increasing efficiency is then still even more important, because then we can support the overall system to take less. So our role here is, of course, we are not a SAF producer, but we are trying to do partnerships to catalyze in the overall SAF ecosystem, because here we are really in that question of creating an industrial uptake which has to be supported. And then maybe let's look as well at the fourth pillar that we call disruptive technologies. So there is, of course, the question, can we completely get into a different propulsion system, propulsion energy? We're looking at hydrogen here, because then we are emitting basically water, and we can cut CO2 emissions to zero if we do it with a fuel cell base, so completely electric transformation of hydrogen. So our goal is to really show that this is possible, and to prepare the technologies in order to make that technology possible to fly in the size of commercial aircraft today. But still, this comes, of course, with a lot of challenges, and I think we might talk about that a bit more afterwards. So we need to use liquid hydrogen. So that means we are talking about cooling it down to minus 253 degrees. Then we're talking about hydrogen. So that's 4 times the volume of kerosene in terms of the energy density. So that means we need to design the aircraft completely differently and rethink the architecture of an aircraft. So it means bigger tanks on different positions. And of course, the overall system needs to be prepared. And it's coming from a technology side with the aircraft. And of course, it's also to be ready in terms of hydrogen availability, the fueling, the overall energy system. So it's a lot about the energy question and the overall ecosystem change. So in a nutshell, for us, decarbonizing aviation is a big topic. So there is a credible roadmap if we take everything together. We need innovation in all the different fields, increasing in efficiency, scaling up SAF, and as well disruptive technologies, as well as operational topics. So this enables us to reach the target, which is the industry has actually committed to drive the emissions down to 0 by 2050. But it only works in a collaborative approach amongst the industry and beyond.
Thank you, Sabine. I'm impressed. I mean, we can feel the challenge and the uncertainty for the entire sector. So let me move to Thierry Poinceau. Sorry, Thierry, for misspelling your name. So you are senior researcher at the Institut de Mécanique des Fluides de Toulouse. You are director of research at CNRS. You are a member of the French Academy of Science and senior advisor at Cerfax, another research lab in Toulouse. So Thierry is leading research on combustion for aerospace and safety application. Your group is performing simulation experiments on existing and future engines for aircraft and power generation. You are studying accidental scenarios linked to fires and explosion. You are the editor-in-chief of Combustion and Flame, the leading journal in the field of combustion, with Professor Egolopoulos from USC. Sorry. So Thierry, I have a question for you. Could you tell us what are the challenges that engineers are facing in the development of technologies based on hydrogen and SAF to propel aircraft?
Thank you. You hear me well? No problem? And you see the screen?
Yes, we can.
Okay. So yes, I just want to give here the position of someone really working on combustion, on the engine, okay? When I look at an aircraft, I only see an engine because I am a combustion guy. And you know that these engines are amazingly efficient. They are actually a big part of the value of the aircraft. And inside this engine, there's a small zone, which is a combustion chamber here. And that's, of course, where everything happens. That's the place where we do this famous CO2. So for the future, the main question is, how do we replace kerosene there? And which fuel can we use? There are many fuels that you can do. You know, chemists can do any fuel. But in practice, when you look at everything which is needed to fly, you end up with only two possibilities to replace kerosene, SAF or H2. So the implications are very important because we know from the automotive industry that usually fuels do not adapt to engines. You have to adapt the engines to the fuels. And that's not a small task. Kerosene is amazingly efficient for all aspects of aircraft. It's very difficult to imagine replacing kerosene simply because it's so efficient. Of course, it's just not efficient for CO2, and that's the problem we have today. So first, to talk about SAF, SAF is almost a kerosene, but it's not really a true kerosene. It's not just another kerosene. There are many issues with SAF linked to what we call operability, the efficiency, the fact that you should not produce too much NOx, too much soot, non-CO2 effects also in the contrails, condensation behind the plane, the capacity to ignite, reignite if you lose the engines, capacity to not quench in certain conditions. So for all this, we are currently learning that SAF do not behave like kerosene. And that's an issue for the people, for the engineers building the engines. Still, going from kerosene to SAF is just an evolution for us, for the engine people. It's not a revolution. It can be done, and there are two conditions. I think Mrs. Klauke mentioned already that availability of SAF is a big issue. The second one is the price. And we would have liked to certify SAF doing exactly the same thing as kerosene, but if the price is 4 times more, we have a problem. So there are some complicated discussions today. For example, we might be able to do SAF at a reasonable price, but by decreasing certain constraints. For example, I don't know, more NOx or more contrails or more difficulties at other places like ignition or quenching. So it's a big topic, but still it's not that difficult to imagine that we can do that in the future. If you go to H2, it's really not the same game. On the paper, H2 burns more easily than any fuel, so it shouldn't be difficult to burn. And in practice, we even burn it today. If you go to industry, you will see that, for example, we burn H2 in rockets like Ariane. So we might say, okay, that's easy, let's just do it. Well, in practice, I'm comparing here Ariane and an A320. They look the same. There are many things which are common, but there's one important thing to realize here. To fill the tanks of Ariane, you need almost 5 hours. To fill the tank of a 320, you only have a few minutes. And Ariane lives for 6 minutes, and the A320 must live for 40 years. So that's not details for the engineers. So it's difficult to say that because we already use hydrogen in a rocket, we're going to be able to use it easily with kerosene, with hydrogen. So moving from kerosene to hydrogen here is tough. There are other showstoppers, of course. The first one is that we don't have green H2. As you know, H2 is just not here. We are producing H2 for the moment with gas, so that's not CO2 free. We don't have the engines for H2, and we'll come back to that in a second. I think we must also mention that H2 is related to safety issues that we probably are going to discuss later today. So there's a report of the French Academy on hydrogen this year in April, which actually discusses these issues linked to hydrogen. And the first thing that this report is saying is that for a while, there will just not be enough green H2 for all people and all sectors who say they can use it. We'll have to wait until we have green H2. But still, in 20 years from today, H2 might be the only acceptable solution to fly. So we'd better prepare for it in any case. And then if we suppose that you have H2 for an aircraft, how will we burn it? Well, there are two solutions. You can use it in a fuel cell for small aircraft, but if you want to propel a big aircraft, we will probably still need gas turbines. Gas turbines today are already used to burn H2, but those are gas turbines sitting on the ground. Okay, you can add any weight you want. So they can work for H2, but if you want them to fly, then you have to put much more weight. And that's not so easy, of course, in an aircraft. So the main issue, of course, is that how do you carry also this H2? You can use it, at high pressure or in cryogenic tanks. This question is solved today. The weight and the volume constraints are such that you cannot use high pressure gas tanks. They're just too heavy. I mean, the plane will never take off. You can do that on a car, on the ground. But if you look here, for example, at Toyota Mirai, which is a car working with H2, to carry 5 kilograms of H2, you need 130 kilograms of tank. Imagine that on an aircraft. I mean, it's not going to fly, or at least not for a big aircraft. So you have to go to cryogenic, but even cryogenic, that's what mentioned also by Mrs. Klauke. Instead of 200 cubic meters of kerosene, you're going to need more than 1,000 cubic meters of H2. So you need to put them somewhere. So this is how you have these ugly planes here on top, or you need to remove passengers. So the tank volume will be an issue. So to conclude on these questions from the combustion point of view, SAF propulsion can happen soon if someone can provide the SAF at a reasonable cost and in reasonable quantities, which is something that is a difficult question. The H2 propulsion is really a long-term project. We're going to have to change almost everything, the plane, the airport, the way we supply it. So it's a much longer term project, and we will need more basic research. Okay, thank you. That's all I wanted to say for the moment.
Thierry, let me stay with you for a few more minutes. You are mentioning the safety issue of using hydrogen. So what solution are you proposing to address the issue?
Okay, that's the second part of my presentation, I wanted to talk about safety issues. And that safety issues is a big question, mainly for H2. Okay, let me put that full screen.
By the way, Thierry, I'm sorry to interrupt you. What about synthetic kerosene, that is producing synthetic kerosene from hydrogen?
Yeah, it's SAF basically, and when you produce SAF, you use some H2 at this point also. The question is really what you carry on the plane, no? And that's the difficult part here. You see one screen or two screens here?
You see the screen.
Okay, so let me change this. Safety up. Okay, let's move now to this question of is it safe or not to go to see the screen?
Yes, we see the screen.
It's perfect.
Okay, so the next question is about safety. Safety is of course something which we have to worry about. And so suppose you're using engines which are fueled by H2, fuel cells or gas turbines. And suppose that you have enough H2. Now, we're going to have H2 everywhere. A basic question now is what happens if you have a leak from some place where there is high pressure H2? It's a question we need to address, okay? It's very different from kerosene. Kerosene will just flow on the ground, you don't worry about it. If you have a high pressure H2 tank, it's a different game. I want also to mention here, because it's not clear for those who don't live in the world of combustion, that for a combustion guy, H2 is not just another fuel, okay? Hydrogen leaks a lot, it attacks the metals, it ignites very easily, it burns much faster than any other fuel, and it explodes. So those are not details when you talk about safety. Of course, it's not negotiable. I mean, safety is mandatory for aircraft companies, and it's true that today we use H2. In industry, for example, in many places. So you might say, oh, we use it in industry, so it can use it to fly. I would just like here to make a joke about that, because as a combustion expert, this is how I feel about this question. Everyone has cats at home, and I think we all understand that having a cat at home is safe, okay? And it's safe also to have tigers in the zoos, okay? But they look the same, you know, 4 legs, a few teeth, you know, and this is like kerosene actually on the left and hydrogen on the right side. But still, no one would go for this, okay, for the moment. And this is exactly the way combustion people feel about H2. We are not fully comfortable with the concept, okay? And the concept actually has already shown that this is a gas station in Norway, 2019. This is a truck station in California. H2 is really biting you, okay? So we need to think about safety. So what can happen? I don't want to frighten you, okay? I'm just giving you an idea of what happens. If you have this tank here at high pressure, and there is a hole for any reason, okay? You can imagine all kinds of scenarios. If there is a hole, then you're gonna have a high-speed jet. When you say high speed, it means supersonic, okay? It's not going slowly, it's about 1,200 meters per second. And this thing leads to fires which are quite different to what people are used. This is a movie by firefighters here, where they have initially a normal car burning, and then they have a bottle of hydrogen inside, and you're going to see what happens when they open the bottle. So here you have a standard fire, I would say, what you are used to, you know, normal flames. But look at what's happening now if we open a high-pressure tank here. You see that it's a different flame, okay? When we say different, for the firefighters, they need to use other tools to quench a fire like this one. So it's not a small difference for us. It's a big one. Now, if we move now to the second thing which can happen is that if you have a high pressure tank which leaks, maybe the gas will not ignite. Then it will mix with the air around it, and later you can have ignition. And if you have ignition, that's called an explosion. Explosions come into two categories, two families. One is deflagration, the other one is detonation. Deflagration are bad, but not too bad. Detonations are very bad. So let me just show you an example of deflagration and of detonation. This is very well known in the field of safety for buildings, for example. Here you have a deflagration. So there is some gas here mixed with air and we ignite it. This is what we call a nice explosion because everyone here is dead, but the building is still in one piece because the pressure wave is small. If you go to detonation, which is the next one, you're going to see a different story. So here, in detonation, you completely vaporize the building. So clearly, if we talk about aircraft, we may accept, for example, to have a deflagration in an engine, but there's no way we're going to have a detonation, okay? So it's definitely not acceptable, and we must make sure that it does not happen. Now, among all the gases, H2 is famous because it's the one which detonates the first, okay? It's very easy to detonate H2. So is that a showstopper for H2? Absolutely not. Anything can be made safe. The whole question is the cost. How much will it cost to make H2 safe in an aircraft is the key question. It's a question which combines research and economics there because it's about the cost. You know, how much does it cost to make it absolutely safe? You don't want one accident here. So that's going to be a big question. Okay, that's all I wanted to say about safety. Thank you.
Well, thank you, Thierry. Thank you for mentioning the problem of the cost, and not only the cost associated to making hydrogen safe, but also the cost of producing hydrogen. So the two issues are important. So let me go back to Sabine. From what Thierry said, explaining the difficulties of developing technologies based on hydrogen and SAF, to go beyond these technologies frontier, do we need, in your view, more public and private financial effort, or more cooperation among industries or both?
Yeah, thank you for that. And of course, your pictures were very impressive. And there is one. I mean, we could go into a long discussion about science and what we need to learn about hydrogen, what is the path. But exactly, you said it. I mean, safety there is no compromise. So that's for sure. If we are going into any technology of a new aircraft, of a different aircraft, it will always be having to be and shall be at least as safe as what we know today. And that's a crucial basic. So I think I've now found how to share my screen with you. Let's see if that works.
Yes, that's perfect, Sabine.
Good. So before we go into that question, what kind of cooperation, private financial effort, public help, I just wanted to make sure that we have this one picture in mind. So do you see that now?
Yes.
Yeah, that's actually where we see all the different animals. You can see the picture. So more than 50%, we need to cover it by SAF, and basically we can start immediately. There is this, there is a part that we can get through operational improvement, and there is a part that we can get through or continuous improvement or disruptive technologies. And that's, I think, what we have to have in mind. If we want to close this gap, you can see how the CO2 emission grows with growth over time. And if we want to bring it to zero, we need to have the different animals here. So if we now go a bit more into this second question, yes, we've seen that the demand for flights doubles every 20 years. So at the same time, we pledge to decarbonize by 2050. So that's what you've seen on the picture. And the challenge is huge. You've seen this, how the opening of the curves. And it's a huge challenge. So we need all the support that we can get. And here it's about investments on one hand and cooperation on the other hand. And if we look across the public and the private sectors, across the industry, as well beyond the industry. And let me give you maybe a couple of examples. And of course, that's also beyond national boundaries. So it's in our industry, beyond the industry, and beyond the national boundaries. So at Airbus, we have a lot of different numerous initiatives and partnerships to drive this tech transformation. Here on the slide, you can see a couple of very different partners. You see exactly that within the industry, with airlines, with suppliers, with airports, but also beyond the industry. So you can see other industries here, and then you can also see how it goes around the globe. And of course, it's not only industry, but it's also research, because there's a lot that we need to learn. And I think we've seen that as well in the explanations of Thierry. So to scale up SAF, we are working with all these different companies and research areas. So airlines, energy companies, investors, institutes, just to name a couple of initiatives. So we have an investment in LanzaJet, who is a leading sustainable fuels technology company. We also have a strategic partnership with Total Energies and also with others on SAF supply, but also on research and innovation. Then, because as Thierry said, there is a lot new standardization to be done even in the SAF field, to be sure that we have standards and an ecosystem which can work together. And an establishment of Sustainable Aviation Fuel Financing Alliance, so the so-called SAFA investment fund, with Air France KLM, who are the ones who use the most SAF today, the Associated Energy Group, BNP Paribas, Berlin Sterling, Mitsubishi Capital Inc., and also Qantas Airways. So you can see how broad the range is of people coming together in order to make the things happen. So that's just a couple of examples of how we try to be our brick into that. When we research on SAF, then it's also about the impact of SAF, because Thierry said it as well. Finally, the engine has to actually adapt to the SAF, and we need to learn a lot. There's CO2, but there's also soot and the different NOxes, contrails. So we are very active in actually learning the impact into the atmosphere. CO2 is one part. On the other parts, we know not exactly as much as on CO2, but there is a balance to be found. And this is why we have different projects. Here, this example shows a test aircraft with a Rolls-Royce engine, in this case, a German Aerospace Center, DLR, doing the research, and actually flying after the aircraft, in this case using SAF from Neste, and actually measuring the impacts in the atmosphere in order to take the right decisions together in this balance. Another other example, if we talk about hydrogen, is here. If we want to drive hydrogen propulsion, then we also reach out beyond our industry. So here you can see actually a test center on a fuel cell hydrogen propulsion system, where we actually use hydrogen, transform it in electrical energy in a fuel cell, and then taking this electric power, control it, and bring it into a mechanical electric engine to do the propulsion. So here we are working with an automotive supplier for the fuel cells, for instance, ElringKlinger, who is an automotive supplier. And end of last year, we were able to play this whole chain up to 1.2 megawatt, which is actually the highest energy which has been able to be produced for kind of an electric aircraft concept so far. So that's just a couple of examples. Another one would be on cryogenic superconducting technologies, because once you have energy, you if you make it very cold, you can have it much more efficient in the transmission of the electric energy. So here we're working with Toshiba, for instance. So there is many areas on which we go in parallel in order to mature. So talking about electrics, we're also looking into battery technologies for hybrid electric aircraft. In our case, you can imagine that, like in your cars, in our case, it would be micro hybridization, because there's only a very small part that we could gain. But there is again trades to be done. And here we teamed up with Renault, for instance, on the electrical path, in order to learn from all the path that has been done already in automotive. Of course, we're talking about very different power and energy classes that we need, but the optimization of the energy management, as well the battery weight improvement, these are things where we can learn. And of course, it goes up to the current cell chemistries, which are still lithium-ion, into the next technology in batteries, which would be the one that we can start looking at, which is solid state, so-called solid state battery design. So here, there is a lot to learn and to be gained. And again, this needs to be looked at across the industry. And I take a last one. Here you can see, if you look even further ahead, and Thierry said that as well, it's a long path. Here we partnered with BMW, another automotive leader, to explore the potential of quantum computing, because all that can be then helped by digitalization and modern ways in order to tackle the mobility challenges. So here it's about advancing fuel cell development through quantum-powered atomic level reaction modeling. So it's going very deep into the chemistry questions and into the design questions of the in-depth technologies. So you can see that all these different examples show that we need very diverse solutions and the diverse actors to tackle the complexities in this big question of decarbonization and the takeoff into the future of aviation. And again, that is a path through very different timelines and very different technology answers in order to get there. So I'm just looking how I can get the...
Okay.
So just a couple of examples of which are the directions and how diverse the paths are. And of course, all the public help in terms of money, in terms of science, is welcome for that.
Sure. So yes, we see. So there are potential technological solution. They are probably more costly and they raise different safety issue. So at this stage, I don't see really the business model for the next 20 years or 30 years. So Mark, going back to you. So we see that technological solution for sustainable aviation available are now on the way. But what are the economic policies or tools that could boost them?
Yeah, so indeed, aviation is going to see its traffic growing, so could be responsible for an increase of carbon emission. But as Sabine said, and also Thierry, aviation is also responsible for many things that we don't like nitrogen oxide, sulfate, root particles. What is I would say satisfying is that we see that there is a lot of effort from engineers to look at solutions for dealing with all this question, this issue. But of course, it seems that there is some way before getting to this technology, to have this technology available. And maybe we economists, we are more short-termist, and in some sense, we have at least, and we think that already we have some tools to help to provide incentive to reduce carbon emission and to boost technological solution. And in fact, Sabine has already speak about that. There are industrial policy measures, but we have also what we call non-market-based measure and market-based measure. And I will say something on each of these measures. On industrial policy measure is, to be clear, is all the type of subsidy policies that will support the investment to develop, and in particular to develop a more efficient and optimized system of air traffic control and air transport management. It is an area where scientific concept and tools exist, and we can use intelligence artificial, large-scale optimization method. It is really an area where the dialogue between engineers and economists can be fruitful, and it is precisely the role of WCTR to provide an arena for such a dialogue. I think that the progress in this area can be significant and can be rapid in fact to develop or to design system that will save in carbon emission. And there is, of course, as Sabine and Thierry spoke, it's all the effort in developing more fuel efficient for aircraft. But of course, again, industrial policy measures in some sense are more, I would say, medium-term solution. In fact, in practical way, there are right now non-market measures to decrease carbon emission. It's airport curfew, flight bans, because they have a direct effect on limiting traffic and so limiting emission. They are relatively easy to implement because in the sense of a policymaker likes this type of measure to ban and to put restriction on mobility, but they are not always efficient. On this slide, I have represented the traffic of cars, trains, and planes on free French market, where a ban of aviation has been imposed. And before the ban, the aviation represented only 5%, in fact, of the total traffic. So, in fact, so there was a ban, but it was almost useless in some sense. Policymakers have banned almost nothing. It's a kind of joke, but it is to illustrate that restraining traffic is not always efficient. Another type of non-market-based measure, and which is related to SAF, is blending mandates. So these policies that is followed by the European Union. So the good things, as Sabine and Thierry explained, is that SAF can be used in existing aircraft technology, and also, which is important, is what Thierry said, on the fuel distribution network. But of course, there are different technology, and their efficiency in terms of reducing carbon emission can be is very dependent of the technology. From the point of view of the economist, considering this blending mandate is finally a kind of tax on kerosene usage to subsidize SAF. As far as I can say, economists are question the economic relevance and efficiency of this policy of blending mandates compared to alternative policy, given the cost of developing SAF. So for the moment, I will say that I will invite a student to look at this question because it remains an area for economic research. So I turn to what we call market-based measure. There are three of type. The one consisting in offsetting emission. Another one which is to directly tax emission. And the third, which is designing a system of trading and keeping emission permit. For the moment, and I think it's very useful to say that the emission trading system that I will describe later cover only 14% of emission of aviation emission within Europe, and then you have about 40% which is covered by CORSIA, by the offsetting system. And so there is 50% of global aviation emission which are not at all regulated. So there is a long way for economists, long way to fight emission from an economic point of view. So let me say something on CORSIA. CORSIA which means carbon offsetting and reduction scheme in international aviation. That it has been adopted by a majority of countries in the world, but it is applied by only a few of them. So until now, it's unclear what the offsets are. So given that we don't know what are the offsets, it's very difficult for economists to evaluate the efficiency of this system. So it is announced that the scope of SCOPIA will be generalized. I don't go into the detail to explain what it is meant by scope, but I will say that most of economists are skeptical about this system to really reduce CO2 emission in aviation, and even some are saying that it is just window dressing. So the second market-based measure is carbon tax. Okay, and so I will just take an example. So we have looked at a market like Paris-Marseille. It's 700 kilometers. On this market, you can have flight, you can have airlines, you can have trains, you can have cars, you can have buses, and you have different type of services. So we can look at the competition between those of this mode. And after having a competition model, we simulate the impact of a carbon tax, significant carbon tax, at taking a level of 250 euros per ton of carbon, which is 3 to 4 times the actual price of carbon. So it's a real significant effect. The simulation shows that the impact of the carbon tax is very efficient because CO2 emissions are reduced by almost 40%. But of course, it has a cost, and in particular, it has a cost of decreasing the market share of aviation by almost 2. So that shows, this simulation shows that the level of the challenge that aviation is facing to maintain its market share, if a carbon tax is imposed in the future. But what is important to say from an economic point of view is that on this example, this high carbon tax is welfare neutral. I explain. The carbon tax raised by the state provide revenue to the state. But there is also the gains that we obtain by the reduction of emission in terms of limiting the damage due to the climate change. And all these benefit from the taxes are able to compensate for the loss supported by consumer, travelers, and the firm due to the tax. In other words, the money raised by the state through the tax and the saving on the damage that it is avoided by reducing the emission can be used to improve the situation of people. We can improve the social condition of poor people. We can provide incentive to buy electric car, or to finance research for sustainable aviation. So carbon tax appear to be is highly politically delicate, but it is economically efficient. Finally, the last solution to give incentive to reduce emission is through the emission trading system that we set up in Europe, and it applies to industry and aviation in particular. Not that China has an emission trading system, which is quite working well. What is ETS? In just a very simple way, it creates a cap on all the emission, and this cap is reduced annually. How it works? On this market, the emitters with higher abatement costs than the carbon price buys emission permits to low-cost emitters. And given that there is a cap, the carbon price, which is the price between supplier and buyer of emission permit, the carbon price tends to increase, and so to give an incentive to high emitter to reduce their emission. The mechanism is probably as affordable as non-market measure for policymaker. It's probably politically more acceptable than setting up a carbon tax. It is efficient, so there are many ways to show it, but we see that since recently, the carbon price has been close to 100 euro per ton in recent years, which is quite significant. The only problem is that the ETS is limited to CO2 emission and does not cover all the greenhouse gas produced by aviation that we spoke before. So to conclude on that is I will recommend the policymaker to boost the support of R&D in the aviation industry and to favor market-based solution in the short time. So thank you for your attention on this question.
Thank you very much, Mark. Thank you for the conclusion. So let me go to my own conclusion before giving out the floor for a final word. Definitely decarbonization of aviation is a necessity sooner or later. First point. Second point, aviation is probably the sector with the largest abatement cost. And third, many people believe that long distance mobility is a fundamental human right. So this trilogy of statement imply quite of a difficulty and the challenges faced by the sector is enormous. So I wish the sector good luck to face it, and there is no possibility of failure. You need to succeed. So Mark, the floor is yours.
Thank you, but we lost Laurie, as maybe Laurie is going to come back. Yes, Laurie. Laurie is the chair of the scientific committee of WCTR Society. And Laurie is going to tell the final words of this panel.
Yes, thank you, Mark. I've been a chair of this conference committee during the conference of Shanghai, or after Shanghai, and then Mumbai, and then Montreal, and this time we will land in Toulouse. It will be fantastic. We have, as Mark said, a community of about 1,500 people, and we expect to have a great meeting also in July. I'm sharing a slide with you, which is about a special interest group that we have, which is specifically on air transport and airports. And I invite you to contact the chair. The details will be shared in the chat, the URLs. Martin Dresner, Professor Martin Dresner from the University of Maryland, or Chika Agamiyoshi, who is now at IATA as head of industry analysis. They are the chairs of this special interest group, and we will have a stream of presentations and papers and seminars also on this topic. If you look at our website, you will find the details of the conference published, which is call for papers in April. You can deliver your papers until September, and notifications to authors about acceptance will be sent out early 2026. And the conference itself will be held from 6 to 10 July in Toulouse. And I will be working with the 33 special interest groups that we have on many, many different topics in transportation to prepare this conference and to prepare the scientific content. I want to thank all the panelists for the fantastic discussion and the very interesting contents presented today. And I hope I can meet you or the audience later on. We will have more of these online seminars in 2025. And also we will be at the Transportation Research Board meeting in January, Washington, DC. So if any of you plan to attend there, please come to visit us at the reception on the Wednesday. Thank you very much, Mark.
Thank you, Laurie. Thank you, everybody. So I just tell you to save the date, July 6th to July 10. We will be in Toulouse to discuss all these topics, but not only on aviation, but also on maritime. We will speak about road, we will speak about logistics, we will speak about optimization of traffic. So a lot of fascinating topics. So thank you very much again, and see you then.
Thank you.
Thank you, everybody. Okay. Mhm. Thank you.
Thank
So-
you.